In today's video, we're going to be taking a look at the one sample t-test and how we can perform this in Python through 5 different examples. We're going to start off with the manual calculation. Then we're going to go through some shortcuts with SciPy and close out the Python coding side of things with a few different graphs. But before we jump into the Python code, I do want to go over a little bit more background information on hypothesis testing as well as t-test. So I'm going to cover a little bit of information on like what is a null hypothesis, alternative hypothesis, the p-value, alpha, and t-statistics, as well as a breakdown of one versus two tail and comparing the normal versus the t-distribution. Tons to cover. Let's start going over with this background information. All right, so a lot of information to cover. Let's go through this one sample t-test before we start coding. So one sample t-test, usually want to compare a sample mean to a known value, which is most likely going to be the population mean. And you want to use a t-test when the samples are going to be less than 30. Now, your t-distribution versus normal distribution, they're very similar, but there's some small differences in them. I have this over here to the right just to show you, right? Our normal distribution over here has thinner tails in comparison to our t-distribution, which is in red. Now, if you guys watched my kurtosis video, this is considered leptokurtic because it has thicker tails, right? In comparison to this normal distribution. And you can see that there's more values that have -4 or -3 or -2 standard deviations away, right? You can see it, that is above. So what are some examples that you can take a look at? So first one would be IQ scores of a sample of data science students. Let's say a class of data scientists, there's 20 students in the class, right? And we want to see if their IQ is significantly different than the population IQ, which would be known as 100. Another example would be if a group of runners is faster than like the average marathon time. So let's say you have a running club that has 10 to 20 people in there, and you want to see if that running club is going to be faster or not. I don't know what the average marathon time is out there. I assume it's like 4 hours and 30 minutes or something like that. You know, the group of runners is probably going to be faster than the average marathon time. And the same side of things of the data science students, they're going to most likely have a higher IQ than the general population. But this would be some good examples where we could test the one sample t-test, right? Before we do jump into going over some examples, there's a lot more definitions that you need to be familiar with. So the first one is going to be null hypothesis versus the alternative hypothesis. Let's take a look at an example of like testing the durability of a new running shoe. So a shoe manufacturer claims that its new running shoe model can last an average of 400 miles before needing replacement. To verify this claim, the company tests a sample of shoes and records the number of miles each shoe lasts before showing significant wear. A one sample t-test is conducted to determine if the average durability of the sample differs significantly from the claimed 400 miles, right? So our null hypothesis, this is what the company's claiming, right? The mean number of miles the running shoes last is equal to 400 miles. The alternative hypothesis in this case is the mean number of miles the running shoes last is different than 400, right? Company claims 400. Our alternative hypothesis is this 400 number is not correct, right? The mean is different. And failure to reject the null hypothesis means the sample mean is not significantly different from the population mean. Now, some other terms that you should know: p-value, which is a probability that tells us whether the difference is significant or due to chance. Significance level, which is your alpha. So typically set at 0.05 or 0.01, which means we're okay with a 5% or 1% chance of being wrong. So how you can think of this, because either questions or whatever in an interview, right, you're going to be asked either confidence level or alpha. Think about confidence level equals 1 minus alpha. So if you have a 95% confidence level, right, your alpha is going to be 0.05 or 5%. 99% confidence level, your alpha is going to be 1% or 0.01. Another term that you should know is a T-Statistics, which is a value that tells us how far our sample mean is from the population mean. And I love this saying because I remember it from high school. If p-value is less than alpha, reject ho for ha. And yeah, it's stuck with me since then from AP stats. So let's talk about one tail versus two tail. So a two-tailed test is used when you're looking for a possibility of a difference in either direction. So above and below, right? The alpha is split between both tails. So for a 95% confidence level, each tail has 2.5% of the rejection region. So let's say our example shoes is 400, right? Our two-tail would be the shoes mean is not equal to 400. It could be 300 or it could be 500, right? Both sides. The one-tailed test is used when you're only interested in determining whether a sample statistic is significantly greater or less than a certain value, but not both, right? Two-tail is both, one-tail is only one side. So that 5% is going to be on one region, right? So the shoes mean is 400. The shoes mean is greater than 400. So we're looking for 450, 500, 550, right? The shoes mean is 400. The shoes mean is less than 400. So again, two-tailed is if you're essentially looking for a value that is not equal to a mean, right? In the 400 case, upper or lower. One tail is if you're only looking for upper or if you are only looking for lower. So here's how you can go through the one sample t-test step by step. So step one is determine the null and alternative hypothesis and confidence level. Then you want to find the sample mean, the sample standard deviation, calculate the t-statistics, find the degrees of freedom and p-value, compare the p-value to the significance value, and make a conclusion. 6 and 7 you can technically combine together, but I just made them as different steps, right? So let's go through our example of the running shoes, right? So sample 5 running shoes was tested in the following miles of where were recorded: 380, 410, 395, 405, and 390. We want to look at a 95% confidence level. Population mean is 400. So step 1 is to define the hypothesis, right? Let me go back over here. We've already talked about this through the null and alternative hypothesis, right? The mean number of miles, 400, versus the mean number of miles is not 400. So we're not going to go through that, right? And then we have the confidence level over here, which is 95%. So we know alpha is going to be 5% or 0.05. Okay. Next, we're going to find the sample mean. So add these together, divide by 5, 396. I'm not going to show you step by step on how to do the standard deviation, but you get 11.94. And now we're going to want to calculate the t-statistic. I have the formula down here to the bottom right. So what we're going to take over here is the sample mean. So 396 minus 400. Then we're going to divide that by the standard deviation divided by the root of 5. I end up getting a value of negative 0.75 on that side of things. Step 5 is to find the p-value and degrees of freedom, right? So on this side of things, degrees of freedom is going to be 4. We get a p-value of 0.494. And again, this is a two-tailed test because we're either looking for above or below. Now we need to compare the p-value to the significance level, which is our alpha. Well, the p-value is greater than that significance value alpha. And if we go back over here, right, if p-value is less, then we reject ho for ha, but we can't reject ho for ha because our p-value is greater. So what our conclusion is going to say is there's no significantly difference between the sample mean of 386 miles and the claimed average durability of 400 miles at the 5% significance level. Thus, the company's claim seems to be reasonable based on this sample. Man, we covered a lot on this side of things, but I think we are ready to code. And feel free to rewatch this before we jump into the coding side, because I do know there's a ton of information covered. But if you are ready, grab a notebook and we're going to start coding in Python. All right, so let's get started. We're going to import NumPy as NP from SciPy, import stats, import matplotlib.pyplot as plt, and finally import Seaborn as SNS, and we should be good to go. So our first example is going to be a manual calculation. So example 1, manual calc, and let's get going. So what we'll start off with is our null hypothesis, and let me give you some context on this once we write these out. So let me say null hypothesis equals 7.5. Then we have our confidence level. Equals 0.95. Let's find our alpha, which if you remember from the slides, alpha equals 1 minus 0.95. Well, 1 minus our confidence level. And lastly, let's have our sample data. So we'll say sample hat sizes equals, and I'm just going to pass in the values that I already wrote for this tutorial. So We'll have all of these over here. Great. And yeah, so essentially what we're going to be taking a look at is hat sizes, right? The factory says that hat sizes are on average for the population at 7.5, but we're going to take a look at this sample down below over here. And based off of the sample, we're going to see if we are going to reject this claim and say that, yeah, the hat sizes are not 7.5. They could be either greater or they could be less. So we're going to be taking a look at two tails for this one, and let's get going. So now that we have everything here for step one, right? Let's take a look at step two, which is calculating the sample mean. So step two, sample mean. So sample mean over here, and let's calculate that. So all we have to do is sample mean equals np.mean, and then sample hat sizes, that. And then let's print out our sample mean. So then we print sample mean, and you can see it is 7.55, right? So a little bit larger, but will that be sufficient enough? We have to go through a few more steps. So step three, we're going to calculate the standard deviation. So calculate STD, and the way we do that is sample STD equals np.std, then pass in our sample hat sizes. So hat sizes, and then DDOF equals 1. And let's print out our standard deviation. And 0.17. Awesome. Now let's go with our next step, which is going to calculate the T-statistic. So step 4, T-statistic. And all we have to do is say T-statistic equals, and actually before I do that, let's find our length. We could run this anytime, but n equals length, and pass in our sample hat sizes. So sample hat sizes. Right, now we have that, and now we can calculate our T-statistic. So we'll say that is going to be our sample mean minus our null hypothesis mean. Divided by, here it's sample STD divided by np.square roots. And did I call this just null hypothesis? No, null hypothesis mean. I apologize, guys. It should be null hypothesis mean. All right, and we should have our T-statistic now. So print that out. And 0.879. Awesome. And for step 5, what we're going to do is find our degrees of freedom and p-value. And the way we do that, degrees of freedom equals n minus 1. Right? Pretty easy there. And I'm not going to print that out, but p-value is going to be equal to 2 times, we'll have over here 1 minus stats.t.rcdf, do an absolute value for our T-statistic, then pass in df equal degrees of freedom. Right, should have that now. And let's find our p-value. So print our p-value out. Oops. There we go. And our p-value is going to be 0.1428 essentially. And now that we have our p-value and we have our alpha, we can conclude this. So what we're going to say is if p-value is less than alpha, print reject the null hypothesis, else print fail to reject the null hypothesis. And you'll see we fail to reject because we have 0.4 and our p-value, or not p-value, but our alpha value is 0.05, right? I didn't print out our alpha, but you go over here and print that out and you'll see it's 0.05. And yeah, that's way smaller than this p-value. So we fail to reject our null hypothesis on that side of things. The hat sizes are pretty close to 7.5. So step 7 would be to draw a conclusion. Obviously, we have this over here. You could elaborate into it for step 7, but I'm not going to write this out, right? There's not really much coding there. But now what I want to do is show you the shortcut method. So we're going to go over here to example 2, and we're going to look at our shoes again. So that manual calculation that we did in the slides, yeah, we're going to make this in just a few lines of code. So shoes, and I'm also going to say this is two-tailed because the example after this is going to be a one-tail and it's slightly different. So our two-tail over here, let's set our alpha value. So alpha equals 0.05. And again, we're going to do 95% confidence level. Pass in our sample data, and I'm just going to copy what I already have. Great. Awesome. We have that over here. And then our population mean equals 400. Perfect. And then what we want to do is we're going to say T-Statistic, and then we'll also have p-value, two-tailed. And this is one thing to watch out for, but when we go to stats.ttest1samp, pass in our sample data and our population mean, this gives us the value of our p-value for a two-tailed, right? And if we want to only have one tail, we take that divided by 2. But since we're doing two-tail right now, this is perfectly fine. So we can print this out, both our t-statistic and our p-value. So our t-statistic is negative 0.75, which lined up with what we had in the video, and or not video, but the slides. And p-value is 0.495. Great, perfect. And now all we have to do is create our if-else statement. And honestly, we could just go over here and say if, and we'll grab our p-value two-tailed. P-value two-tailed is less than alpha, right? Print reject null hypothesis, else print fail to reject null hypothesis, and you'll see it's failed to reject null hypothesis because 0.49, much greater than 0.05. But that's going to change in this next example where we go over one tail, and we're going to reject our null hypothesis because I made sure with the data. So let's jump into that right now. All right, so let's take a look at example 3. So we're going to say example 3, and we're going to look at is compare the rookie batting average to the leagues, right? So our null hypothesis may be something like the rookie batting average is the same as the leagues, and then our alternative hypothesis would be rookies batting average is less than the league average. Now, because it's less than, right, we're going to look at one tail. And I could do the same thing and say the rookie's average is greater than, again, would be one tail. But if I go and say that the rookie batting average is not the league average, then we take a look at two tail. So less is the key word over here. And let's get started. So also, I want to mention that I'm going to do a 99% confidence level. So all the other examples I've showed you guys have been 95%. This is going to be a little different. So let's start off with that. So what I'll say is alpha equals 0.01, right? And we'll say rookie batting averages equal. And let me just pass in what I have over here on my example code. So Feel free to use numbers however you want, but I have 210, 230, 160, 240, 200, 235, 225, 185, 275, 240, 225, and 215. Pause the video if you have to. Put in whatever numbers you want. If you want to have something different, regardless, that's what I have over here. All right, so I just ran that. Now let's find the mean on that. So we'll say mean rookie average equals np.mean, and then pass in our rookie batting averages. And I'll just print this out over here. So print mean rookie average 0.22. All right, and now let's grab our T-Statistic. So T-Statistic and also our p-value. And that is going to be over here, value two-tailed, right? And this is where it's going to start being different a little bit. So I'm going to say stats.tTest one samp, and then pass in our rookie batting average, and then the mean rookie. So rookie batting average, and then our league average, which I actually didn't paste this in. So I apologize on that. League average is going to be 0.25. So league average 0.25. And I'll put these in here now. And it's not. Yeah, so we have our rookies batting average and then also league average, right? We get our T-Statistic and p-value. But this p-value is not done, right? You'll notice I said p-value two-tailed. Well, by using stats.tTest one sample, it gives us the two-tailed version. We need to divide this by 2. So all we have to do now to get our real value is p-value one-tailed equals, and we'll have our p-value two-tailed divided by 2. And this is what we want to have, our p-value one-tailed. Awesome. And let's print out our points over here. So T-Statistic, negative 3.527. And then let's print out our p-value. Print out our p-value one-tailed, 0.002. Awesome. And let's keep moving forward. What we're going to do now is draw our conclusion. So I'm just going to paste what I have over here. If our p-value is less than our alpha, reject the null hypothesis. The rookie average is significantly different from the league average. I should say significantly lower instead of different from the league average. And then else fail to reject the null hypothesis. There's no significant difference between the rookie's average and the league average. And you'll see, well, I didn't change my code. Let's put in our p-value one-tailed over here and reject the null hypothesis. The rookie average is significantly lower than the league average, right? 0.02, right? This is way lower than this over here where we have our value of 0.01. So awesome. This worked as expected. Now let's go and make some plots. So if you don't want to plot, skip ahead to the outro. Otherwise, let's just jump through a few of them. So we'll say example 4 is a box plot. So box plot. And in over here, what we'll have is plt.figure. We'll set our fig size equals 6.5. SNS dot box plot data equals rookie batting averages np.full. I'm just gonna paste in what I have over here. We have np.full, length, rookie batting averages, league average, palette set 2. Then up next, we'll set our ticks. So plt.xticks 0, 1. And we'll have here rookies and league average. All right, and then title, plt.title, rookie, batting averages versus league average, and then PLTY label. It's gonna be our batting average, and then show. And I'm just gonna paste in that second line that I have here. All right, so box plot data, rookie batting averages, np.full, length, rookie batting averages, league average, and then palette, it's gonna be set to. There we go. So you can see the league average is right over here, right? Most of our values are gonna be essentially, let's say that's 021 to 0235. We do have our one outlier, right, at 0.16, and that is our box plot. Now what I want to do is take a look at our next example, which is going to be our 99% confidence interval. And let's do that. So example 5, which is our 99% confidence interval. And all I'm doing on this one, I'll just paste in the code on here. Fig size, we set an error bar, right? And actually, let me write my 2 lines above because we didn't create our standard error in the confidence interval. So we'll say standard error equals stats to SEM rookie batting averages, and that's going to give us our standard error. And then what we need to do is create our confidence interval. So confidence interval can be equal to stats.t.interval 0.99 length rookie batting averages here -1 location mean rookie average scale equals std error. Should be it. And I'll just copy over my code. Awesome. And then what we're going to do is plot this out. So fig size, right? Error bar, H line, and let's plot this out over here. And you can see we have our 99% confidence interval at 0.25 lies slightly outside of it, which is why we're able to reject this. And lastly, right, and this is the rookie mean average. See how far it gets. It gets pretty close, but not fully there. Lastly, what I want to do in our last example, man, I said last and last example, but example 6, we're going to plot the t distribution in T-Statistic. I'm just going to paste this in here. We can walk through this code. So line space, we set our t distribution PDF over here, figure, plot, x t distribution, right? Set our critical value. We're filling this over here, and then just setting our titles, X label, Y label, and our legend. You can see over here, right, our T-Statistics -3.53, which just to show you again, going back up over here, right, 353. Our critical region, so that's anywhere alpha less than 0.01. And then our T distribution. Yeah, so those are 3 graphs as well as our 3 examples to walk through. So just go through this one more time. We had our first manual example over here, right? Quite a bit of work. And then if you want to do a shortcut, we have our T-Statistic and p-value that we can grab from t-test1 sample, pass in our sample data, and then our population mean. Now this gives you the 2-tailed p-value. So if you do want to get only 1-tailed, you have to divide that by 2. And then that'll get us our one tail. Then I showed you a few different graphs you can make, right? You can have a box plot over here to see how rookies compare to the league average. Then over here, we have the 99% confidence interval. And right, we plotted this out. Make sure you grab your standard error and find your confidence interval before plotting that. And lastly, showed you a t-distribution where we pass in our t-statistic, showed plotting of the critical region over here, and then just plotted the t-distribution. And yeah, that's it. I'm just going to pause on here so you guys can grab this code. And I hope you guys enjoyed this video. I'm going to be making others on more hypothesis testing because there's a lot of variance to this. Hope you guys enjoyed this video on the one sample t-test. And if you got some value from this video, make sure to subscribe. One of our goals here is to reach 100,000 subscribers in 2025. And we're uploading multiple data science focused videos every single week. Now, this video covers specifically statistics. And if you want to watch more videos in our statistics playlist, we have videos linked down below in the description, and you can click onto the playlist right over here.